Okay, so yeah, so I saw recently that that this sort of this what am I working on today? So there's this project zkLib um, that I guess is sort of mainly being driven by this guy Kwong, and the goal of it is to do these sort of formally verified snarks or proof systems, and so this is up my alley. It's something that I've like heard a lot about before, and like so I guess this whole thing is sort of being funded um, wholly or partially by the Ethereum Foundation, and is a part of their effort to do some sort of formally verified things for zk VMs. Um, and so I was looking through it, and I saw that I knew that that like this concept of like computable polynomials was something that was necessary, and it looks like they've done a lot of cool work to get that to be possible with this unipoly type. Um, and I also saw that like the connection to these like regularly defined in mathlib polynomials is down here. And this is something that I wanted to complete, so I've been working a little bit on this. So maybe I'm going to try and like finish this sort of ring equivalence between the unipoly type, which is just sort of arrays, and this type of polynomials with a degree bound. Okay, so the left inverse is done. I've done the left inverse here, and I'm going to do the right inverse part now, or I'm going to try to. Right, so right inverse, what we have to show um, is that the right inverse of a tropically bound polynomial, and like so this is the conversion to, and this is the conversion from. So if I unfold that, basically just have to do this introduction. Right, so if I unfold right inverse. Oh, this is interesting. So I guess right inverse is defined as something else as a left inverse. Fold right inverse. Function.right inverse tropically bound polynomial. This is actually just very funny to me. I'm going to go to the definition and appreciate this. Yeah, so apparently like G is a right inverse of F if F is a left inverse of G. Who knew? But maybe I'll just unfold both of them just so that it's clear when people put their cursor there that's what's happening. Basically, I have to prove that for all inputs, if I do both functions, then I get that same thing back. And I can intro the polynomial and the bound. And now I have to prove that these things are equal. And one thing I can do is unfold here. But really what I want to do, so I want to do some sort of like, yeah, so I unfold, I simp, but I do this extensionality thing. Because there's two things that I really need to prove. So clearly this is a type of tuples, right? The first part of the tuple is a polynomial. The second part of the tuple is like the bound. And I need to prove that they're both the same. So I can do extensionality, and that will split into tuples, one for each side of the tuple, presumably. And I can like simplify both things probably. So, right, I have to prove something about the first component of this, but I simplify, and then that gets rid of that part. And so really it's just a question about if I map all of these coefficients to this degree bound, array range, degree bound, tropical, untrop of bound, yes, okay. The coefficient of I, basically I need to prove that the coefficients are always equal. So let me think about this. Maybe there's some like theorem that needs to be applied here. So what I'm doing is I'm taking a unipoly and I'm making one out of a particular array, and then I'm converting it to a polynomial. This is the function that converts it to things. So if I go to definition here, I can see that the conversion to polynomial in question is by evaluation. So yeah, like some theorem along these lines would seem to make sense. Coef2poly, for example. Like if I convert it to a polynomial and take a coefficient, that's the same as taking a coefficient, which is exactly what I'm doing. So what if I just add this? Oh, apparently I need like the namespacing. Unipoly, right? But that doesn't really simplify it all the way. Right, so I have this I, But I feel like there's something missing here. I feel like there's missing like a statement that I should be less than the degree of the polynomial, right? Right inverse. Yeah, there's something off here, right? This is not like quite the right statement. I feel like I encountered this before. This was like an early version that I like had typed wrong, because really it should be a subtype of this that it's equivalent to. It's a, yes, so this is a sub-semi-ring of Rx in the tropical polynomial. Because these are polynomials, right? But clearly the bound has to be less. So I feel like that's missing that. So the question really is, can I take this and say that this is the thing that you want to be working? Type mismatch, right? So there's a type mismatch because this two tropically bound polynomial, we go to definition, is of this type. But really, I don't want that to be the type, right? Really, like if I'm converting a unipoly to a tropically bound polynomial, it should be of this type, right? Right, it shouldn't be of this product type. It should be of this type. Now there's a type mismatch because there's an additional thing that I have to add, which is right. So how do I basically I want to say that this is going to be the type of something. Maybe I need to enclose this in parentheses. I use this. And then, yeah, so this is the last thing, so sorry. But what happens if I now try to show term for this? Show term. Sorry. Yeah, okay, so this is starting to look more exactly like what I want. This, and then sorry. Yeah, so here's where I have to prove the fact. I, for example, unfold tropically bound poly. Need to simplify, so it's like mem carrier. I need to show that it is a member of the carrier, right? So this is a sub-semi-ring. So to be a member of a sub-semi-ring. Is it possible to just do apply and find a correct thing? Refine. Sub-semi-ring, mem. No, that's not what I want. This is what I want, basically, right? Yeah, so, yeah, I think that's correct. Now can I sim? Okay, apparently this simplifies back to the initial form. I think that the reason this is being complicated is that if you know what you're doing, you can just proceed with the rest of the proof. Unknown identifier, tropically bound poly, tropically. Okay, unfold that. Simp. Okay. d.toPoly.degree is less than p.degree bound. Okay, that looks like something that I could maybe prove. The poly to degree. Right, so this is a matter of unfolding to poly. Yeah, so this is the length, essentially. And now I wonder if there's something where I can do where there's a theorem about the eval2 being less than, the degree of eval2 being less than something. Because eval2 is essentially a sum, right? Unfold unipoly dot eval underscore 2, right? Array fold L. Yeah, really this is like an array fold L. Let me go to the definition here. Right. So this is just a very convoluted way of saying that we're summing this array over something. This is just an array. Is there really no array dot sum? Let me go to the docs. Array dot sum. Yes, there is. The sum of an array. And it's defined as, okay, fold R, so it's defined slightly differently. So I worry I would break everything. Or maybe I can just make a theorem, right? This is the accumulator. So what's the lemma? Lemma. Eval2 equals sum. Is this the exact right lemma? P dot eval2 equals p dot sum, but the problem is it's not sum in the normal sense, right? Maybe like it has to be like map sum or something like this. P dot map dot enumerate dot map something. I don't know. Does enumerate? Yeah, array dot enumerate. What's the name of that particular function, I wonder? Array enumerate. But the problem is that that's not the name. Okay, so let's go to Lugal actually. Lugal. We want something that takes an array of A's and returns an array of something else, namely nat, an array of nat times A. Can this be found for me? Maybe if I just ask for something that takes an array of one kind and returns an array of another kind. Yeah, that's most of what this is. And maybe I can also ask that nat be somewhere present. Maybe also that prod be somewhere present. This is looking at zip index. Okay, so this is just exactly right. So zip index was already here. Okay, but this is even stranger. Okay, so like the question is, why do we write fold L this? Like we could have written this in a different way. Here's what I'm claiming. The same function implemented with map and sum. Right. Okay, so what I'm saying is I'm going to do p.zipIdx.map, right? So yeah, so I'm going to map over the function that takes ai and returns f of a times x to the power I. That is now a particular array. Yeah, that makes sense to me. This just seems like a little bit more of a natural implementation, but perhaps there's some performance reason why the other way is better. Right, and presumably there's some way of proving this relatively easily. Like the question now is like unfold sum, right? So unfold everything. This is array.sum that we want to unfold over, right? The only, like really the only difference is that it's very similar indeed. But to like return all the way down here, if I simply use this, right, this is now bugged. But if I like try to use this to prove something, right, so rather than unfolding eval2, what I want to do is I want to say rewrite unipoly.eval2, val equal eval2, fail to synthesize boolean ecar. Does that theorem require this? Certainly it does. It's one of those things where it's like classical reasoning. It's failed to synthesize. Now I can unfold eval2 prime. And now there should be some theorem about the sum. So this is a polynomial. No. Okay, apparently not. Nevertheless, there should be some theorem about how the sum of a bunch of polynomials. Yeah, so sorry, no, this is a polynomial. And then there should be something about how apply polynomial dot sum degree LE. Something like this. Polynomial degree LE. Degree sum LE, okay. Okay, I got the order of degree sum LE. Okay, now it's taking forever to load, which is spooky. Not sure why it would be taking forever to load. Tactic apply failed. Failed to unify. Okay, just a sec. Failed to unify something, sum. Oh, this is like a thin-set sum, right? Whereas in my case, we have an array sum. This is an array of things. Yeah, so what needs to happen is there needs to be perhaps a variant of this theorem or like all of the other, set likes. Polynomial array, maybe like a list sum, degree list sum. Right. So what I need to do is for a particular list, right? One point is that array sum is the same as this particular sum of lists. And another point is that the degree, so we just have to prove that all of the degrees are less than the bound. All right, again, in theory, we shouldn't need this because it's non-computable anyway. We should be able to like say classically that there exists a Boolean equality instance, something like that. Okay, so let's think. So the list in question is this one, but the problem is it's not going to be able to. I want to like refine this. Finally trans this, and then some other thing, application type mismatch, right? And the point is that I want to make you decide on what your first argument is. Right, yes, but it doesn't know how to do that. I can also like define it alternatively. Right, so if L2 could be like array.zippindex to list. This is cheating. But whatever, so now it doesn't know how to synthesize the placeholder. Now it's like completely comfortable perhaps, right? So now we just have to define, okay, what happens if I just write this? Okay, I'm a little confused. Why am I being told I have an additional goal where I have to find a unipoly, right? List.map, right, at the maximum. And after this, yeah, I don't know exactly what's going on here. It's not like there's any like, yeah, I just have to show that it's less than this degree bound, right? What happens if I like proceed with the proof? So all I'm doing is proving something here. This dot map in that degree, right? Okay, no, that's not quite right. Why is there a net degree here? Okay, so apparently this involves a degree. Why does this have to involve a net degree? Couldn't I, let me go to the definition here. Net, yeah. I'm mapping the net degree. Something's a little weird here. What if I put this here? So this should be a list of nets, and I take the maximum, which gets me a withbot n. The degree here, of course, is a withbot n, right? I mean, it's sort of funny because like what we could have done, right? If all of these polynomials are zero polynomials, we could have mapped degree over those polynomials and gotten a list, right? Degree takes a polynomial to a withbot n. Go to the definition of degree, right? So we could have gotten a withbot n. To go back, I don't know where I am. To go to this particular theorem definition, it says that if I take a sum of some polynomials, the degree of that polynomial, which is a withbot n, is less than or equal to the list map of the net degrees L over. So there should be like an analogous theorem. This is for products of lists. That's not what I want. What I simply want is a theorem that says that for any element of the list, the degree of the sum of the list, no, that's also not right. What I want is to say that if every element of the list has a degree less than some withbot n, then the sum of the list entire has that degree bound as well. So maybe this calls for like a PR to mathlib, for example. Right, let me see if I can like pull up mathlib here. Yeah, just a sec. Okay, so here I am in mathlib. So I've been making changes to master, which is never good. So I think this is like some pull requests I was working on like improving documentation. Polynomial induction. Yeah, this is like this thing that had like three things in a row, three like primes in a row. This is like a insane lemma name. So why don't I just say create a branch, Tim Bailey, and polynomial add induction on. That will be the name of this. Cool. That's perfectly fine. Changes it, and I might as well publish the branch, for example. Now I want to go back to master, and I want to go to mathlib algebra polynomial big operators. Right, okay, mathlib algebra, I think I said polynomial next, right? Polynomial big operators, and list degree, yeah. Degree list sum LE. So I wanted a different version of this theorem that does not involve a degree. Yeah, just a sec. Like, because this is for products and sums, and this is for sums and maximum. So the problem is that maximum takes a list of alphas to a withbot alpha, and what I need is a function that takes a list of with bot alphas to a with bot alpha, which returns bot if the list is empty. Can I just do like some do notation there, perhaps? Okay. Degree list sum le prime maximum le map maximum. I want this is to be a degree, not a degree, but a degree. Okay, like, so question 1, is this being interpreted sensibly? This is a with bot n. No. So what I need is like, is it like this or something? You know, like this in Haskell, I think is how it's written. Unidentifier list.maximum. Sorry, it is list.maximum, right? It's not maximum L to width. Right. This is not what I want though. I feel like I need to clarify that this should be that this side should be with bot type mismatch, has degree with bot, but is expected to have type with bot. Isn't there like some name for this in like the theory of monads? Okay, clearly Lugal is required. I need with bot, and to with bot. Yeah, I mean, unknown identifier with bot, I spelled it wrong. Right, with bot. But the thing that I want to do is be able to like reduce it. How is it defined, by the way? Is it like just defined immediately in terms of with top or something? With bot. Yeah, the canonical map from A into with bot A. It's just option A. So is there something where it's like option A? Option A, or anything that takes such a value. Join, yes, join is what I want. So maybe over here, what I want is to say dot maximum dot join. Right. It all feels like a rather convoluted way to just say that if every single element of the list has a value less than this value, then the sum has a degree less than the value. Right, so previously on this episode, we were doing this. We were using this theorem where we were equating to net degree, but we would rather not do that in any way. Yeah, so like, what happens if right, so this is, let me just leave this as a sorry. Let me just write the theorem as I would want to use it, right? This is the version of the theorem that I would want to use. Degree list sum LE of degree for all degree. So the thing that I want to conclude is we have L, and I am claiming that HL for all P and L, degree P less than N, where N is a natural, N is this, N is a natural number. No, it's actually a with bot natural number. And from this, I am to conclude that the sum is less than N. Sorry. By induction on L. L with something. Right, this is not how it's done anymore. No, simp with induction L with. Should this be like no or something? Be like a cons, like this. No follows by simp, and then for the cons, I simply simp, and I apply the add, the lemma with the add, which was defined over here somewhere. No, not over here. It was like degree add LE. Add LE, yeah. Apply LE trans, degree add this, something else. Right, so now I just have to prove this. And now I like simp at HL, and then our case is HL with whatever, HL, HT, HTail, and now I can put that in the in this one, right? Which is specialize the noctis hypothesis with HTail, and now exact should figure it out for me. Yeah. So that's basically the theorem I want. So this is important, right? I argue that this version of the theorem is important because it relates the degree to the degree rather than the degree to the sum. And I wonder if I can like more easily prove this now. So what I want to just do now is say apply that. Cool, easy. Intro, HMM, PHP, yes, right. And I mean, so what I need now is a way of proving that this is less than the maximum because it's a member of the set. Yeah. The thing is, I don't know if anyone ever does this like option join maximum thing. Yeah. I don't think that any of these are going to be correct. So perhaps if I submit this, people will say that I should do the other theorem, but I don't necessarily need the other theorem. Right. On the other hand, like, you know, maybe if I add the other theorem, people will say, why do you need this extra theorem? So I'm just going to submit this as is. Okay, so I'm going to create a new branch, which is daily degree list some degree, and just add that. Commit. Publish branch. Okay, so now presumably there's like a whole ton of things on GitHub for me to create things for. Can I sign in for GitHub, please? Sign in. Okay, just a moment. I don't actually have my thing with me. Just a sec. Okay, I'm back. MATLAB for this one. Right. Compare and pull request. Good draft pull request. I can go and add the things later. And I can return here. And I can draft pull request. Cool. Okay, so now that I have both of these drafts, I can maybe elaborate about them. Okay, so this is the old one. I can go and like fix this later. This is the, sorry, pull requests, author, Bolton Bailey. This one, yeah, so this one. We can look at the changes in another tab. This is where I'm just adding this theorem. Okay, so edit. Adds a lemma relating the sum, right? Of the sum of a list of polynomials to the degree of the polynomials. Like the other thing, what is the name of the other thing? Of the sum, right? Like this one, which only relates this to the not to the sum, but yeah, to the net degree of the polynomials in the list. Found. Wow. To contribute to zkLib. And maybe I can copy this. Maybe I can select this. And
comment. And I can edit this, and I can say feet. And I can also go and look at the format. The format is like feet, and then and then I set the file name. Okay. So in this case, the file name is algebra polynomial big operators. As lemma. The lemma has a really long name. Okay, that seems fine. We can remove the draft status. And this will presumably build. Yes, I only add one declaration. Okay, let's just look at it to make sure that there's nothing obvious. Stare at it for several seconds. We have L, N is a width bot N. For all P and L, the degree is less than N. The degree sum is less than N. Induction L, nil, cons. Okay, well, obviously it's going to complain about the simp. So let's fix that. Okay, that's over here. Sorry, line 76. So I need to do this. In fact, I can maybe move this later, right? No, I can't move it later because I can transform it to a rewrite though. Okay, this is another simp question mark. I specialize, and then I exact. And like if I really wanted to, I could golf it like this. Right, so I apply this. I could bring this up to the beginning because it's more naturally at the beginning, right? Because these are the things, right? So like the first thing I do is unpack my inductive hypothesis and my HL, right? So like HL is the same as saying these two things. I can unpack those things and then I can proceed. So that looks like it makes a little bit more sense. Okay, I think that's fine. Golf, commit, sync. Yeah, probably there's some other dumb thing about this that I need to change, but I'm just not seeing it. Right, I mean, I guess you could say that one thing I could do is show term here. Yeah, that golfs it a little bit more. Cool. Cool. Okay. Any more golf that I can do? Can this be a rewrite? Perhaps. guess not. Yeah, okay, I think that's basically fine. Okay, so we did not end up making progress on zkLib, which is somewhat to be expected. Nevertheless, we added a theorem to our ever-growing list of mathlib pull requests, so at least some forward progress was made.